Okay. The machine, the course is mechanical design. Now let's know the design, the implementation of machine. A machine is a combination and other components that transforms, translates, or uses energy, load, or motion for a special purpose. This is arc welding machine and cutting machine, spot welding machine, handing machine, and sewing machine, braiding machine. The machine is comprised of power source, transmission, and control parts. Let's for a car, the power source is engines and materials, and the transmission system is couplings, catchers, shafts, powertrain, and the control system is steering systems, brakes. A machine composes individual machine elements, and the components are classified as universal elements such as bolts, case, splines, pins, belts, chains, gears, and bearings and springs, and special elements such as turbine blades, crankshaft. The universal elements are widely used in different kinds of machines. This is the key point of this course. This is the classification of machine elements. The basic requirements for machine design reverse
sharp
and safe.
Sharp.
Safe and
Safe.
This is sharp. Sharp is a mechanical part. Sharp. You know the gear sharp.
Safe and reliable performance.
It's E, not E. It's E.
Oh, E.
Yeah.
E, okay. And analyze and calculate the stress and strains of the parts, and choice of materials, and structural design, and processing properties, and code and standards. Okay. A multitude of considerations are summarized in this table. For example, for an component, the safety and the reliability, we should consider the load strength, deflection, and stability. And for a component surface, we should consider the friction, wear, corrosion. the main content of this course. You should be familiar with engineering materials and their properties, material selection, heat treatment, manufacturing processes, and the knowledge of turbulence, fluid mechanical, heat transfer, electric and information technology and controls, and creativity, complex problem solving capability, and the CAD. Do you learn the course CAD?
Computer aided design.
Yeah.
Okay.
Okay. So you should have some prerequisite course, engineering materials. Do you learn this course?
Yeah.
Okay. And theoretical. Height. For example, the composition of this alloy when it melts is liquid with the temperature decrease. The austenite forms in the liquid. With temperature decrease, the austenite forms, and in this point, there is a reaction. The austenite transform to ferrite and cementite. Okay. Carbon steels is the alloy contains iron and carbon. With the carbon content different, we can classify the carbon steel into low carbon, medium carbon, and high carbon steel. We also call this composition alloy as eutectoric steel, and in this area, the carbon content is less than 0.77%. We call them hypereutectoric steel. And in this area, the carbon content is between 0.77% to 2.11%. We call them hypereutectoric steel. Low carbon steel. In low carbon steel, the carbon content is less than 0.3%. It's low carbon steel. Low carbon steel is relatively soft. The medium carbon steel carbon content is between 0.3% to 0.2%. High carbon steel, and the carbon content is less than 1.7%. Okay, This is the microstructure of ferrite. In our alloy, the atoms arrangement orderly. Okay, orderly. The atoms.
Yes.
And we choose this unit cell, and the material can regard as the repeat arrangement of the unit cell. Okay, so in ferrite, the atoms occupy the color of the cell and the body center of the cell. This is the ferrite. And it has a body-centered cubic structure. Ferrite. And the interatomic space are very small, so the solubility of carbon is very low. It's very low. This is the solution of carbon in ferrite. The max content is 0.218%. This is the structure of Australite. The atoms occupy the color of the unit cell and the face center of the cell. It's different from the ferrite. It is the stable form of pure iron at temperature between 910 degrees Celsius and 1400 degrees Celsius. The auxilite is soft and ductile, and so is well suited for manufacturing process such as forging. The face-centered cubic structure of iron has large interatomic space than in ferrite. Even so, in FCC means the face-centered cubic. In FCC structure, and the maximum solubility is only 2% of carbon. Delta iron, we also can call it high temperature iron. It's also a BCC, body-centered cubic phase. The carbon steel and cast iron complete iron take before rotting. And elasticity is the deformation of a material undergoing non-reversible change of shape in response to applied force. And elasticity is the property of a material that returns to its original shape after stress that made it deform or distort it removed. And breaker is when subject to stress, it breaks without significant deformation. And stiffness is the resistance of an elastic body to deformation. And durability is the ability to endure force without elastic deformation. And roughness is the quality of being unpleasant to the sense. Hardness is the resist penetration by a shape object. And toughness, the ability of a material to absorb energy and plastically deform without fracture. We define the engineering strain as the change in length divides the original length, and the engineering stress sigma, then it's the applied force divides the original area. The tensile test, and the tensile stress is measured by a tensile test. In the test, first pull the material and elongate it and reduce its diameter. This is the typical test sample, and this is the tensile test machine. The sample is mounted between the two bricks. And then increase the tensile load. This is the beginning of the test, and the uniform elevation and reduction of cross-section error, and this is continued elongation, and this is lacking begins, and the load begins to decrease and fracture, and finally the length will be measured. The beginning of the test, And in this point, in this error, there is a uniform elongation. Continue elongation, lacking break. This is a stress and strain curve. From O to P, it's elastic deformation, and in this area is plastic deformation. The elastic deformation is temporary, and the plastic deformation and the elastic deformation is you can measure and point P is proportionality limit. Point A is elastic limit. At this point, the material stops behaving elastically and begins to have plastically. And when the stress is moved, the material doesn't return to its original length. The yield point. At this point, the material shows a large increase in strain for a small increase in stress. From O to P, the simple extent in direct proportion to the load applied is satisfied the Hooker's law. From P to E, the material reaches its elastic limit. Up to the elastic limit, the steel will regain its original length when the load is removed. From A to S, after elastic limit, the steel will not regain its original length. S is the yield point. From S to B, there is a rapid increase in length for each increase in load. Up to B, there is no change in the cross-section of the steel. The maximum load is reached. And from B to K, the simple length filter but the load force. And after K, the simple filament fracture. This is the stress and the strain curve. Elastic part. In the elastic deformation, the elongation of material responds to the stress in a linear fashion, and the rod reverts back to its original length upon relief of the load. the modulus of elasticity equals strength divided strain. The modulus of elasticity reveals how stiff a material is. Yield strength separates the elastic region from the plastic region of material. Plastic part, permanent deformation. The tensile stress is the highest force that a material can sustain. And ductility. Ductility is measured of the amount of plastic deformation a material can undergo under tensile force without fracture. We can express as hardness. Hardness is account for abrasion resistance as well as resistance to denting. It's directly related to strength. The harder a material, the stronger it is.
Let's do a small experiment.
Okay, let's begin. This is part 3. It's about heat treatment. Heat treatment is used to produce the microstructure and mechanical properties that we needed. And when heat treatment, we will heating the material and then holding for a time and cool. This is the process of heat treatment, and an object of heat treatment material is to impact certain desirable properties. The former the heat treatment include annealing. Annealing is heating a steel and holding for time and then cooling it very, very slowly. There is a C cover. The horizontal axis is time, and the vertical axis is temperature. And this curve is transform curve. And if we cool the metal very slowly, for example, for a carbon steel. If we pour it very slowly, we call it annealing. And the microstructure of the carbon steel after annealing is perlite. If we cool it very fast, we call it quenching. And the microstructure after quenching is martensite. Martensite. There are some different types of annealing. For annealing, process annealing, and spheroidal Dyson. Luminogen, the cooling rate of luminogen is higher than annealing. And the carbon steel after annealing is very soft, and the mechanical properties of the carbon steel after quenching is very hard. The quenching may increase the strength and hardness of material. The hardness that can be obtained from a given treatment depends on the following factors: quenching rate, carbon content, and work issue. With the carbon content increase, the tendency of quenching is increased. Rapid quenching needed to harden low carbon and medium plain carbon steel. Water is generally used as a quenching for these steels, and also for the high carbon steel we can use oil. Temperature after quenching, we usually use the temperature. After tempering, the material will become more plastic and ductile. And so there is some properties. Let's say a medium first. Hypoelectroid steel is perlite and ferrite, or perlite and cementite. Yes, it is perlite and ferrite. So the hypoelectroid steel is the steel with carbon content more than 0.77%. So the microstructure of hypoelectroid is perlite and cementite. The cementite can increase the strength and hardness of the steel, and the ferrite is soft. Ferrite is BCC structure, and austerlite is FCC structure. So the deformation is very easy with this structure. So when forging the steel, we always heat the steel in this area. After annealing, the microstructure of carbon steel is after annealing is cooled very slowly. So the microstructure is
Ferrite.
Perlite is a mixture of ferrite and cementite. So it's perlite. After quenching, the microstructure of carbon steel is quenching means cool the steel very quick, and so the microstructure is its microstructure after quenching is because the cooling rate is very quiet, so confusing of the atom has low time for the carbon or iron atoms to diffusing, so it may form the martensite. Martensite is very hard and brittle, so if use the gear surface need hardness, so we are quenching and form martensite in the surface. This is martensite. And the hardness of annealing high carbon steel is lower or higher than that of quenching high carbon steel. Yes, lower. When the high carbon steel after annealing, the microstructure is perlite and cementite, and quenching is martensite. Martensite, the microstructure is martensite. So the hardness of annealing high carbon steel is lower than that of quenching high carbon steel. Yeah. Okay. So today the class is over.
Thank you.
Okay.
Thank you, Roshi. Ask about the